Welcome back. Today we are going to derive a radar range equation, which relates the range of radar to the characteristics of transmitter, receiver, antenna, target, and the environment. First, we will discuss an isotropic antenna. Isotropic antenna. This antenna, which radiates uniformly in all directions, radiates uniformly in all directions. Power density at range R from this antenna, which is isotropic antenna, from power density at range R from this antenna will be equals to transmitted power, which is the peak power, divided by the geometric area of the sphere, 4 pi r square. But in radar, we don't employ an isotropic antenna. We use in radar systems, or system application, we use a directive antenna to concentrate energy into a particular direction. So in our radar systems we employ a directive antenna, not omnidirectional or isotropic antenna. So the gain of an antenna, maximum antenna gain, will be equals to power density, maximum power density of a directive antenna divided by also the power density of a lossless isotropic antenna. So the power density at range R from an isotropic antenna, power density at range R from a directive antenna, will be equals to power density of an isotropic antenna multiplied by the antenna gain, PT, multiplied by the maximum gain, divided by 4 pi r square. Now I am going to introduce the characteristics of the target, which we call radar cross section of the target. It's a characteristic of the target that includes in radar range equation. So RCS, or sigma, which means radar cross section of the target, RCS, which means radar cross section of the target, denotes by sigma. This is the power density returned to radar from power incident on the target. The power density returned to radar from power incident on the target, denoted by sigma. So power density at range R from an isotropic antenna at the target will be equals to power density of the target will be equals to PT multiplied by G divided by 4 pi r square multiplied by sigma. But the power density returned to radar will be equal power density at the target. Power density at the target. But power density returned to radar will be equals to PT, transmitted power, multiplied by the gain, multiplied by radar cross section, divided by 4 by r square, divide also 4 by r square for the targets. Now we're talking about return power density return to radar. Now I'm going to turn to talk about received power. Received power, which means PR, will be equal to power density returned to radar multiplied by the effective area of the antenna, will be equals to previous P multiplied by the effective area of the antenna. I mean this one. So it will be equals to PT multiplied by G sigma multiplied by AE divided by 4 by square R fourth power. So AE effective area of the antenna will be equals to AE effective area of the antenna will be equals to PA multiplied by A, where PA is the efficiency, aperture efficiency of the antenna, aperture efficiency of the antenna, and A will be the geometric area of the antenna. Geometric area of the antenna of an antenna. The antenna in meter square. So returned power at radar will be equals to PT multiplied by antenna gain multiplied by the radar cross section. The radar section depends on the shape of the target rather than its geometric area, multiplied by the effective area of the antenna will be equals to PA multiplied by A, whereas PA is the aperture efficiency of the antenna, A is the geometric area of the antenna in meter square. Now I'm going to also that the maximum range of the target can be described as the maximum distance beyond which the target are not expected. Maximum range of the target. Maximum range of the target. Range of the target can be defined as the maximum distance is the maximum distance beyond which targets are not expected, cannot be detected. Not expected or target cannot be detected. Targets cannot be detected. Beyond which target cannot be detected. It occurs when received power equals to minimum detectable signal. This is received power at radar. This is the minimum detectable signal. So a maximum range of radar is the distance beyond which the target cannot be detected or are not expected. It occurs when received power will be equals to minimum detectable signal, PR equal to S minimum. Now by plugging S minimum instead of PR in the previous equation, we can rewrite the previous equation. R maximum will be equals to transmitted power, it's the peak power multiplied by the antenna gain, multiplied by the effective area of the antenna, multiplied by the radar cross section of the target, divided by 4 by square S minimum. This equation is called the fundamental radar equation, or the basic radar equation. The basic radar equation. The basic radar equation, the fundamental radar equation. We also know that there's a relationship between the antenna gain and the effective area of the antenna. G will be equals to 4 by AE divided by lambda square. The relationship between antenna gain and the effective area of the antenna for monostatic radars. Monostatic radars, which they employ a single antenna for transmission and reception. So by replacing G by this value in this equation, we can get another formula, or by replacing AE equals to G multiplied by lambda squared divided by 4 pi. This will be 2 second. This will be the third one. So by plugging 2 in one, we will get another formula of this equation, and by plugging 3 in this one, we can get another form of the radar maximum radar range. This formula is considered to be the fundamental one, but it doesn't take into account all other consideration. We are talking about the receiver noise. We don't mention it in here. We will talk about it later on. We will talk about also the fluctuation losses, the system losses, the attenuation coefficient, propagation constant, many other factors, the average power, and so on. These all considerations must be taken into account. So the range, maximum range, calculated by this formula is only the half of the actual range, because we have to take into account all another consideration. This will be a special chapter for all other parameters or the phenomena that will be added to this formula in order to take all consideration, including fluctuation losses, system losses. We are talking about system losses also, system losses. We're talking about attenuation coefficient, propagation constant, and so on, and the average power. So we'll talk about this later on. We have just to put in mind that this is called the fundamental radar range equation with the basic form. So another consideration, and again I have to remind you that the range calculated by this one will be only the half of the actual or predicted one, because we have to take into account many other consideration like the internal noise, which will be the thermal noise, will be taken later on, talking about system loss, fluctuation losses, and many other parameters also. This is the main radar range equation. Thank you for following me. I'll be glad to answer to your question. Bye for now.